Have you ever wondered what a planet orbiting the sun and a football flying through the air could possibly have in common? Well, it turns out they both follow the exact same simple set of rules. Today, we're going to dive into Newton's 3 laws, the fundamental rulebook that governs pretty much every single movement in our universe.
It all starts with the most basic question you can ask. Just imagine a ball sitting on the grass. What does it take to get it moving? What's that secret ingredient that kicks everything into action?
And of course, on the flip side of that, what makes that same ball, once it's rolling, eventually slow down and stop? The most amazing part is that the answer to both of those questions is exactly the same. So let's figure out what it is.
Okay, to really understand the rules of how things move, we first need to get to know the main character in this whole story, a little something called a force. You can kind of think of it as the invisible hand that's directing this whole cosmic play.
At its heart, it is incredibly simple. A force is just a push or a pull on something. You push a toy car, you pull a wagon. That's really it. But what those simple pushes and pulls can actually do, well, that's where things start to get really fascinating.
So a force is basically an agent of change. It can start something moving, like when you kick a football. It can stop something moving, like a catcher's mitt stopping a baseball. It can change an object's speed, or its direction, or even its physical shape, like when you're kneading dough. A force is anything that changes what an object is currently doing.
So now that we have a feel for what a force is, we can jump into Newton's first law. And what's so brilliant about this rule is that it actually starts by telling us what happens when there is no force at all.
Okay, so that's the official textbook wording. But what does this unbalanced part mean? Well, think of a game of tug-of-war. If both sides are pulling with the exact same strength, the rope doesn't move, right? The forces are balanced. An unbalanced force is a push or a pull that isn't canceled out by another one. And without that, things just keep on doing whatever they were already doing. An object at rest stays at rest, and an object in motion stays in motion. And this tendency has a very specific name.
And that name is inertia. A really good way to think about inertia is just laziness. An object is inherently lazy. It wants to resist any change to what it's doing. And the more massive an object is, the more inertia it has, which means the lazier it is and the more it resists change. So in a way, the first law actually gives us our definition of a force. A force is simply whatever you need to overcome an object's inertia. Okay, so law number 1 tells us we need a force to overcome that laziness, that inertia. But how much force? That's the question that Newton's second law answers for us. It gives us the math. But before we look at that famous equation, we need to add one more piece to the puzzle. And that piece is called momentum. You can think of it as the quantity of motion, or maybe the oomph, that an object has. It's a combination of two things. How much stuff is in an object, that's its mass, and how fast that stuff is moving, that's its velocity. It just makes sense, right? An object with a lot of momentum is going to be way harder to stop. This is something you already know, just from living life. Imagine an elephant and a bicycle, and they're both moving at the exact same speed. Which one is going to be harder to stop? The elephant, obviously. Its huge mass gives it an incredible amount of momentum. You would need a much, much bigger force to change its motion. And all of this brings us to one of the most famous equations in all of physics. Force equals mass times acceleration. F equals ma. It is so simple, but so powerful. To change an object's motion, in other words, to accelerate it, you need to apply a force. And the bigger the mass, the bigger the force you're going to need. This one little formula governs everything from launching a rocket into space to just throwing a baseball. So we know what forces are, and we know how to measure them. But there's one last crucial rule. Forces never, and I mean ever, act alone. As Newton's third law tells us, they always come in pairs.
I am positive you've heard this one before. For every action, there is an equal and opposite reaction. It's famous for a reason. It means you literally can't touch anything without it touching you back with the exact same amount of force.
So here's the most important part to get. If you punch a wall, you're applying a force to the wall, right? That's the action. But at that exact same instant, the wall is applying an equal and opposite force back on your hand. That's the reaction. And that is why it hurts. The forces are equal in size, but they're acting on two different objects. One's on the wall, and the other is on your hand. Okay, we've got our 3 laws. Now let's put them to the test and try to understand the most universal force there is, gravity. It's really the perfect example of all 3 of these rules working together in perfect harmony.
Gravity is the force that pulls everything with mass towards everything else with mass. So the Earth is pulling down on you right now. But according to that third law, you are also pulling up on the Earth with an equal and opposite force. It's wild. And because gravity is an unbalanced force acting on you, the second law tells us it causes a constant acceleration, and that's why things fall.
And this brings us to something people get mixed up all the time: mass versus weight. Your mass is the amount of stuff you're made of, and it's constant. It never changes, no matter where you go in the universe. Your weight, though, is a force. It's the force of gravity pulling on your mass. So if you were on the moon, where gravity is much weaker, your mass would be exactly the same, but your weight would be much, much less.
So there you have it. Inertia, F equals ma, and action-reaction. 3 beautifully simple laws that completely decode the motion of everything in our universe, from planets all the way down to people. The question isn't really how things move anymore. The real